which significantly enhances the dynamic performance. Abstract. This paper presents a novel combined brake pressure control algorithm for improving the precision and timeliness of pressure system of electric commercial trucks. The algorithm Keywords: high-speed on-off valve, regenerative braking control, pressure tracking, fuzzy control, simulation, experimental test. Acknowledgement. We have taken efforts in this project. However, it would not have been possible without the kind support. We would like to extend my sincere thanks to all of them. We are highly indebted to Electrical Department for their guidance and constant supervision, as well as for providing necessary information regarding the project and also for their support in completing the project. We would like to express my gratitude towards the teacher of Electrical Department and our team members for their kind cooperation and encouragement which help us in completion of this project. We would like to express my special gratitude and thanks to all persons for giving us such attention and time. Our thanks and appreciations also go to our colleague in developing the project and people who have willingly helped us out with their abilities. Table of contents. Cover page. Title page, point 2. Acknowledgement, 3. Abstract, 4. List of tables, 6. List of figures, 6. List of abbreviations, 7. Chapter 1, Introduction, 1. 1.1 Background, 1. 1.2 Problem Statement, 2. 1.3 Objective, 2. 1.4 Scope and Limitations of Project, 3. Chapter 2, Literature Review, 4. Chapter 3, Methodology, 6. 3.1 Schematic Diagram, 7. 3.2 Algorithm, 7. Chapter 4, Expected Outcomes, 9. References, 9. Chapter 1. Introduction. Background. The topic of the paper is the development of a combined brake pressure mechanical friction system is essential for achieving optimal blending braking performance. 1. Pneumatic braking pressure control is typically accomplished using proportional valves with a digital control scheme. However, the high cost of proportional valves limits their practical application in commercial vehicles. As a cost-effective alternative, on-off valves driven by pulse width modulation, PWM, are widely used in the braking control system of commercial trucks due to their good pressure control capability too. These algorithms aim to improve pressure control accuracy, stability, and efficiency. Some studies have investigated pulse width modulation with sliding mode controllers, pressure different limiting modulation control methods, traditional PWM control methods, switching sliding controllers with fuzzy logic controllers, and a comparison of hardware and software-based controllers. While these studies have achieved improvements in control performance, challenges such as nonlinearity, hysteresis, overshoot, and malware still exist in on-off valve control systems. It starts by developing a nonlinear mathematical model of the target on-off valve control system, which includes an electromagnetism model of the valve and a hydromechanics process of fluid delay characteristics. The model is validated through experimental tests. Next, a novel combined control algorithm is proposed, incorporating an incremental proportional anti-co-differential (PID) controller using PWM signals and a fuzzy controller using cooperative PWM signals from. The algorithm enhances control accuracy and timeliness by driving valves in different modes and balancing the pressure through mode switching. Local simulations and experimental tests are conducted to validate the algorithm's Problem statement. The regenerative braking system in electric commercial trucks requires precise and timely control of brake pressure to optimize its performance. Existing control algorithms for pneumatic brake pressure control in commercial trucks face challenges such as nonlinearity, hysteresis, overshoot, and valve wear. Proportional valves with digital control schemes are effective but expensive, limiting their practical application in large-scale commercial vehicles. On-off valves driven by pulse width modulation. However, the dynamic performance of on-off valve control systems can be further improved to enhance the overall braking performance. The goal is to that overcomes the limitations of existing control algorithms and achieves precise and timely pressure tracking for the regenerative braking system of electric commercial trucks. Objective: maximize energy recovery during regenerative braking. Optimize braking performance for operation. Develop a specialized trucks. Account for factors such as vehicle speed, load, road conditions, and driver inputs in adjusting brake pressure. Ensure adaptability and scalability of the algorithm for different electric commercial truck models. Contribute to the overall efficiency and performance of electric commercial trucks in commercial applications. Scope and limitations of project. The proposed system has some scope and limitations. Scope. The proposed algorithm focuses specifically on pneumatic brake pressure control. It aims to optimize energy recovery and braking performance in these vehicles. The algorithm will be designed to be adaptable and scalable for implementation in various electric commercial truck models. Mathematical modeling, algorithm design, and simulation testing will be provided to limitations. The proposed algorithm is tailored specifically for pneumatic brake systems and may not be applicable to other braking technologies. The algorithm's performance may be influenced by the accuracy and reliability of the input sensors and data used for real-time adjustments. The success of the algorithm may depend on the availability of compatible hardware and software in electric commercial trucks.
Real-world testing may be limited to specific operating conditions and scenarios, and results may vary in different environments or with different driving styles.
The proposed algorithm does not address other aspects of the electric commercial.
Chapter 2. Literature Review.
Efforts related to pneumatic of the regenerative.
Of energy conservation and environmental protection. It emphasizes the need for effective control algorithms to ensure optimal braking performance and energy recovery efficiency in commercial trucks. Several studies have been conducted to develop control algorithms for pneumatic brake pressure control in commercial vehicles. Kitradi and Najati
proposed a pulse width modulation with sliding mode controller for pressure tracking, demonstrating improved pressure control performance compared to other controllers. LBETAL presented a pressure different limiting modulation control method for regenerative braking systems, achieving a linear hydraulic pressure control performance. One ETAL study. Despite the progress made in previous studies, challenges such as hysteresis,
overshoot, and valve wear still exist in on-off valve control systems. The literature review emphasizes the need for practical and effective solutions to enhance the dynamic performance of braking pressure control. Overall, the literature review provides an overview of existing research in the field of pneumatic brake pressure control algorithms for regenerative braking systems in electric commercial trucks. It highlights the achievements and limitations of previous studies and sets the stage for the proposed novel algorithm presented in the paper. Chapter 3. Methodology. In this study, the researchers focus on a typical mechanical brake-by-wire system used in electric commercial light trucks. They specifically examine the pneumatic regenerative braking system, using a schematic diagram to illustrate its structure. The system includes two fast on-off valves, an inlet valve, and an outlet valve. The inlet valve is placed upstream of the left wheel cylinder, while the outlet valve is positioned downstream of the right wheel cylinder. These valves are normally closed. When the driver presses the electronic brake pedal, the braking intensity is determined, and the regenerative braking controller sends braking distribution commands to the on-off valve controller and the driver motor controller. These commands include the request for pneumatic braking torque, TB_REQ, and the request for regenerative braking torque, TRE, based on the braking signal and vehicle information. The total braking torque required for deceleration is a combination of the actual regenerative braking torque, TRE, actual pneumatic braking torque, pneumatic. Achieving accurate and rapid buildup of pneumatic braking pressure is crucial for ensuring excellent deceleration performance of the electric truck. The researchers provide a sectional view of the valve to illustrate its internal structure. This type of valve is equivalent to and two-way valve in various components such as considering the inlet valve. When the coil is energized by a driving voltage, the electromagnetic force moves the valve core upward. In this position, an orifice opens, allowing airflow between the high-pressure supply and the air chamber of the wheel cylinder. On the other hand, when the coil is de-energized, the return spring restores the valve core to its downward position, blocking the orifice. Consequently, the airflow is prevented from passing through the orifice, maintaining the pressure in the air chamber. The outlet valve operates in a similar manner. In simpler terms, the researchers investigate the pneumatic regenerative braking system in electric commercial trucks. They analyze the structure of the system, which includes on-off valves placed before and after the wheel cylinders. These valves open and close to control the airflow and, consequently, the pressure in the wheel cylinders. When the driver applies the electronic brake, commands are sent to the valve and motor controller to regulate the pneumatic and regenerative braking torques. By understanding the functioning of the valves, the researchers aim to improve the buildup of pneumatic braking pressure, ultimately enhancing the overall braking performance of electric commercial trucks. Figure 1. Schematic
Schematic diagram of the pneumatic regenerative braking system. Algorithm. Initialize the algorithm parameters and variables. Set the initial brake pressure value. Continuously monitor and acquire real-time input data, and driver inputs. Ensure accurate and reliable data acquisition. Calculate the kinetic energy of the vehicle based on its mass and velocity. Update the kinetic energy estimation as the vehicle speed changes. Determine the desired amount of energy to be recovered during regenerative braking based on the vehicle's kinetic energy. Calculate the optimal brake pressure adjustment required to achieve the desired energy recovery. Compare the current brake pressure with the optimal brake pressure calculated in the previous step. Adjust the brake pressure and optimal values. Consider the dynamic response of the pneumatic brake system to ensure smooth and controlled pressure adjustments. Continuously monitor the braking performance, including factors such as stopping distance, stability, and driver comfort. Fine-tune the brake pressure adjustment to optimize the braking performance while maintaining
the desired energy recovery. Repeat steps 2 to 6 continuously in real time to adapt to changing driving conditions and maintain optimal brake pressure control during regenerative braking. Analyze the energy recovery efficiency, braking performance, and system stability to validate the effectiveness of the algorithm. Based on the evaluation results. Chapter 4. Expected outcomes. The expected outcome of further studies in this research would include investigating the effect of valve parameter variation on the proposed control performance. This would provide insights into how changes in valve parameters, such as response time or flow characteristics, impact the overall control accuracy and effectiveness of the pneumatic valve system. Additionally, conducting more real vehicle tests of the valve control system would allow for a comprehensive evaluation of its performance and validation in real-world scenarios. By addressing these areas, the research aims to further enhance the control algorithm and optimize the braking system, ultimately improving brake safety and brake feeling in electric commercial. References.
I hope you get the summary of this paper. Thank you. Please subscribe the channel. Till then, bye bye.